Hello everyone, and welcome back to If It's Math. Today we're going to continue our series on real numbers as part of our Fundamentals of Algebra content. You remember in part 1 of our real number series, we talked through the basics of number sets, including how to define them and how to determine union and intersection. But in this video, we're going to talk about some very common number sets that you're going to be encountering throughout your journey in algebra. So things like rational numbers, prime numbers, real numbers, and what all that represents, how you define them, and then understanding how you use them in algebra. So by the end of this video, you'll be able to define and explain a whole bunch of different number sets and discuss how they relate to each other. But before we jump into that, just want to do a quick recap of some of the important things that were covered in our first video on set notation. So here we're talking about common number sets today. So it's important to remember what a set is. And remember that a set is just a collection of numbers. That's all that it represents. So it's all in how you define it, because saying a set of numbers has no meaning until you've defined what that set is. So today, again, we're going to go through some common definitions of ones that you're sort of going to be expected to know without people defining what that means. So when someone says rational number, you're going to need to know what that is. So remember, that's all a set is. So when we talk about those today, that's what we're defining. And then there were a couple of key symbols that wanted to just remind you of. So remember, U was the union. And so what that represented, let's say we have the set A union B. The result of that would be any number that is in A or in B. So the important thing with union is that it's or. Then we had the companion that was intersect. So that looked like the upside down U. Remember, that was intersect. So if we were saying A intersect B, that's all numbers that are in A and B. So that's that key difference there. So when we're talking about our union, we're in or. We're talking about intersect, we're in and. So it's going to be important because we're going to talk about how we put some of these sets together. One other symbol I wanted to refresh on, another set of symbols, was this, which remember meant subset. So if we say that A is a subset of B, that means that any number that's in A is also in B, but there are numbers in B that are not in A. So they're not the same thing. Everything in A is in B, but B is not the same thing as A. And then the last one was empty set. So it's like that O or 0 with a line through it. And the empty set is the set with no numbers. So those are the important ones to refresh on. So we've got our union, our intersect, our subset, and our empty set. And with that, we're going to be able to jump straight into some new symbols for today. So just a few that we need to talk through. One just looks like a little dash, but this is complement. And the way to think about complement is that if you're talking about the complement of a set, so let's say A prime, so the complement of A, what that is the set that is opposite. So that's the key element of complement. Complement really tells you opposite. So that's the key part of it. So for instance, let's say that we had the set A, where A is the set of numbers x, such that x is greater than 0. So if you wanted to have the complement of A, it's going to be the opposite. So it needs to be every number that's not in A. So if you think about this, then it's going to be the set of all numbers x, such that x is less than or equal to 0. So again, complete opposites. So let's think about this in terms of intersect. So if we do A intersect the complement of A, that will always equal the empty set. That's actually the definition of complement. So remember, complement, main thing you need to be keeping track of, that complement means opposite. Okay, two other symbols, and they're related, is this, which represents element. So up till now, when we talk about intersection or union, we've been talking about how two sets relate to each other. But what about a number and a set? So that's what element gives you. So what element means is a member of. That's the way to think about what it means. So, as an example, let's say we have the set of numbers A, such that A is all x, such that x is even. So then what we know using our symbol is that 2 is an element of A. Oops. 2 is an element of A, and that's how you would write. So going along with that is going to be not an element. So that symbol just tells you that whatever number is before it is not a part of the set after. So if we keep our A defined as all even numbers, if I give you the number 3, you would say that 3 is not an element of A. So that's all the new symbols for today. We've got complement, element, and not an element. Okay, so let's start looking at these number sets. So the first thing you're going to notice, probably jumps right out at you, is these funny capital letters. So I call them super capitals. Whenever you see something like this, where it's a capital letter, but there's some extra lines in it, like if you look at the N, you've got these 2, you look at the W, you've got that in there, that's telling you this is a standard set. So this letter means a set that we all have agreed to what that represents. So you'll see them throughout the video today. So the first one we're going to do is natural numbers. So natural numbers represent the numbers that we use to count things. So if you had a basket of eggs, it would be the numbers that you're using to count those up. So really what it's going to give you is starting with 1, 2, 3, 4, 5, and so on forever. That's all there is to natural numbers. So just the numbers that we use to count does not include 0. So that's an important one to remember because that's what another set is. So N does not include 0. Or another way to represent that, remember, is that 0 is not an element of N. Because if 0 is an element, what you're actually in then is your whole numbers. So these whole numbers is all of your natural numbers that we just talked about, and it also includes the number 0. So then if you think about all the members of that set, really, you're just adding in the 0. 0, 1, 2, 3, 4, 5, and so on forever. So another way, thinking about our set notation, is that W is also N union 0. Right? So key difference between these two. Natural numbers does not include 0, but whole numbers is all the naturals, including the number 0. So N for natural, W for whole. So they're going to get more complicated. Those are pretty straightforward, but that gives you a sense of where we're building from. So the next one, you might have already heard this term before, is integers. And these integers are going to be represented by this, fancy double-lined Z. So what integers are is every positive and negative whole number. So when we did whole numbers, they were all positive. But if you included if they were negative as well, that's going to give you your integers. So we don't have any fractions, we don't have any decimals, it's just all those whole numbers on that number line. So Z is going to be all the numbers before it, -3, -2, -1, 0, 1, 2, 3, and so on forever. So again, just positive and negative numbers. So most of the time when people talk about numbers, they're actually talking about integers, even if they don't realize that's what they're saying, because these are the numbers that we use, every day of our lives. We use negative numbers, we use positive numbers, but fractions and decimals aren't what a lot of people think of with numbers. Okay, so the next one is even numbers and odd numbers. And of course, I know you know what even numbers are and odd numbers are, but the important thing here is how you can write them in set notation, because you might have to do that. So if we think about even, the way it's technically defined is that it's all integers that are divisible by 2. So there's the key piece there. all integers divisible by 2. So let's think about how to write that as a set, because I can't just write them all out. And you don't want to do a pattern in the set notation. So you wouldn't want to say, brace -4, comma -2, 0, because it's not really clear all the time what that pattern is. So we need to figure out a way to write that. So what we're going to do is some new notations here. Ready? So our even numbers, and there's not a standard fancy capital for it, is we know what we're trying to get to is -6, -4, -2, 0, 2, 4, 6, and so on. One key part here is that 0 is even. But if we think about how to write that in set notation, we want the set of all numbers x that are integers. So that's a shorthand for how you can do that. So set of all x that are elements of z, which means all integers, such that when you divide that x by 2, the answer is also an integer. All right, did you catch that? There's a whole lot written in that little phrase, that little mathematical phrase. So we have that even numbers is the set of all integers such that when you divide that integer by 2, you end up with an integer. That's what that tells you. So you get that whole number component when you divide it by 2. Okay, so then we've got our odd numbers. So think about odd is just all numbers that aren't even. But in the definition piece, we've got all integers that are not divisible by 2. So when we start to think about how to write that in set notation, we're going to have that set of all numbers x that are integers such that when we divide x by 2, what do you think? It's not an integer. So all integers such that when you divide them by 2, you do not end up with an integer or a whole number, essentially. So that's where you get those parts. So that is the technical definition of even and odd numbers. And if you need to write them in set notation, that's how you can write them. Okay, so our next set of numbers that we're going to take a look at is our prime numbers and numbers that aren't prime. So with prime, again, there's not a letter that really represents this, but the key here is primes. So that is all natural numbers. So remember, natural numbers don't include 0. So natural numbers greater than 1 that are only divisible by itself and 1. So natural numbers greater than 1, divisible by itself and 1, and that's it. So let's list some of these out, because there's really no way to write a rule for it. So 2 is prime, 3 is prime, 4 is not because it's divisible by 2, it takes you to 5. 6 is not because it's divisible by 2 and 3, gets you to 7. 8 and 9 and 10 are all divisible by something. Then you jump to 11, 13, 17, and it just goes on forever. But the thing that all these numbers have in common, again, is that you can only divide it by itself and 1. So 7, you can divide by 7 and 1, and that's it. 17, 17 and 1, and that's it. So one quick note about 2. 2 is a special case because 2 is the only even prime. Any other prime number that you see is not going to be even. 2 is the only one. So composite numbers isn't something that people talk about a lot, but it's important just to know what you call a number when it's not prime. And that's all that a composite number is. So natural numbers greater than 1 that are not prime. So that's going to give you 4, 6, 8, 9, 10, 12, and so on forever. And so that's the definition of a composite number. So really the important thing just to know about it is that the composite is the opposite of a prime number. If a number is not prime, it is composite. Okay, so next we are up to positive integers. And again, I know you know what these mean, but how do we denote that? and then also what is the special notation for it. So remember, z represented our integers. So z with this positive, or this plus up to the upper right, so it's like superscript addition sign, that is going to represent the set of all positive integers. So that's all integers that are greater than 0. So that's going to be 1, 2, 3, 4, 5, and so on forever. So if you need the formal set notation for it, you've got the set of all numbers x that are integers such that x is greater than 0. That's how you get all those components. So all integers greater than 0. So negative integers are going to be the same space. We've got that integer with the negative off to the side. So we've got our -4, well, starting forever, -4, -3, -2, -1. And again, thinking about that set notation, the set of all numbers x that are integers such that x is less than 0. Okay, so up till now, we've only been dealing with numbers that look like whole numbers: -7, 8, 14, 23, 862 million. But we all know that fractions exist. Sometimes we wish they don't, but fractions do exist. So rational numbers is when we start to bring fractions into the equation. So rational numbers are represented by the fancy q, and they're all numbers that can be written as one integer divided by another. That's the key. So in fancy math words, it's the quotient of two integers. So there's no real way to write these numbers out because it's anything. There's an infinite number of rational numbers between 0 and 1. So we can't just sit here and write out a set of them. So we have to think about how to really define it using our set notation. So we're going to say, okay, so let's figure out how to break this down. So Q is going to be the set of all numbers x that can be represented as P divided by Q, such that P is an integer and Q is an integer. But there's going to be one key thing here, right? What do we know that you can't do? Can't divide by 0. So Q is not going to be able to equal 0. So we've got our P is an element of Z, Q is an element of Z, and Q does not equal 0. So that is how you define a rational number. So if you want to put this in English, we've got all numbers that are written as one integer divided by another integer without the bottom being equal to 0. That's how you define a rational number. So the fact that there's a rational number kind of begs the question, is there an irrational number? And there is. So what irrational numbers are, kind of in the definition, anything that's not rational. So it's any number that can't be written as one integer divided by another. It might seem a little strange because you might say, well, aren't all numbers like that? But they're not. But these are always represented with some kind of special symbol, or you actually use a letter to represent the number because you can't actually write the number. So, a good example of this is square roots, right? So the square root of 2. You can't write that number, what that actually equals. It goes on forever, and it doesn't repeat in any way. It just keeps on going and going. So it has to be represented with this symbol. So this is kind of giving you a clue sometimes that you might be in the situation of an irrational number. Another very common one is pi. So the number pi that you use all the time in geometry, that's an irrational number because you can't write it out in numeric form. It goes on forever and does not repeat. One you might not have gotten to yet, but you might eventually, is E. E is another very common number that is one of these irrationals that you just can't write it out. It goes on forever, does not repeat. So if we think about how to define this, you can't write all of them out. So you're just going to have to use that set notation where we've got the set of all numbers x such that x is not irrational number. So that gets us finally to the point of this whole video series of real numbers. So real numbers, and it's going to sound kind of anticlimactic because you've been building up to it so far to figure out what they are. All a real number is, our fancy double R, is a number that is rational or irrational. So any number that is rational or irrational is a real number. And you put those together and you get all real numbers. So if we think about this in words, we've got the set of all numbers x, such that x is a rational or an irrational number. And that's the definition. But we've got a few other ways to do this, right? Because that's not nice and mathy. It's too many words. So we need to figure out how to get that into a different type of set notation. So we've got our set of all numbers x, such that, let's turn this into symbols. If we say x is a rational number, x is an element of Q, or an irrational number, x is an element of P. So our real numbers, all numbers that are rational or irrational. But we can take it one step further just to make it even simpler. Think about R, if it's any number that's rational or irrational. That's all you have to write. Q union P, because Q is our rational numbers and P is our irrationals. So now we've got our real numbers. So any of those special numbers that go on forever, or any good old-fashioned regular number that can be written as one number divided by another. And that's it. That's what real numbers are. So we talked about a whole bunch of sets. So I wanted to do just a quick little recap of what they are to hopefully help reinforce this and make it a little more natural. So let's see how fast I can do it. So we've got our natural numbers. So that's going to be going from 1, 2, 3, 4, and so on forever. No zero, right? That's one of the keys to naturals. For our whole numbers, you add in 0. Get our integers in. So where we're finally bringing in our negative numbers, remember? -3, -2, -1, 0, 1, 2, 3, so on forever. Our positive integers, starting with 1, 2, 3, 4, 5, and so on forever. Our negative integers, starting forever, -5, -4, -3, -2, -1. Remember our rational numbers. So this is P divided by Q, where P and Q are elements of Z, and Q does not equal 0. So our irrationals, so this is all numbers that are not rational. Like, there's really no better way to write it. So not rational. And then when we had our real numbers, remember this was our rationals and our irrationals together. So that's really all there is to those number sets. So we sort of talked about it throughout, but these sets do relate to each other. So a lot of them nest inside one another, and I'm a visual person, so it really helps me to see all these coming together and what it represents. So let's say we want this bubble to be all real numbers, right? So we're going to say, okay, so this is all reals. Everything here inside this bubble is going to be all real numbers. So we had two big divisions, right? We had our rationals and our irrationals that made up our real numbers. When we looked at our rationals, we had integers, whole numbers, natural numbers, a bunch of them. So thinking back to the previous shortcut list that we looked at, the smallest set of numbers that we had really was those natural numbers, right? So that was 1, 2, 3, 4, 5, so on forever. Well, when we wanted to add in our 0, we had our whole numbers. So if you think about the visual nature of this, every natural number is a whole number, but there are whole numbers that are not in that natural number set. So we took it a step further. Remember, we got our integers, because what we know is that all of these numbers, these whole numbers and natural numbers, are also integers, because integers gave us our positives and our negatives. Then we took it a step out from there, one farther, where we had our rational numbers. And that was, remember, two integers divided by each other. And then the only thing that's left is our irrationals. So this is just a visual way to see that, right? So we have our rational numbers as all of these irrational numbers plus all of these rational numbers. But when we think about the rational numbers, well, there are integers in there, there are whole numbers in there, and there are natural numbers in there. And every number that's a natural number is a whole number. Every number that's a whole number is an integer. Every number that's an integer is a rational number, and every number that's a rational number is also a real number. So that's how they all kind of nest inside of each other. And guess what? That's it. That's all there is to these common number sets. So now you know all about natural numbers, whole numbers, integers, composites, primes, rationals, irrationals, real numbers. So hopefully this has helped you see what those sets are, what they represent, how you can write them in set notation if you need to. So I hope this was helpful. Please like this video if it was. Subscribe to our channel to be the first to know about any new content. And always remember that if it's math, we have the solution.